Welcome to our next video, which is all about determining the formula of a compound. So when we're given a formula for a compound, there's really two different options for formulas we could be given. We could be given the empirical formula of the compound, or we could be given the molecular formula for a compound. And it's important in order to distinguish the difference between these two, especially because they both have their importance in chemical applications. So the empirical formula is usually less common, but it is seen when you're trying to determine what is the formula of a compound via an investigation. And the empirical formula is the simplest ratio of elements in a compound. The simplest ratio. So that would just be, what would be the lowest ratio that's given? How many carbons are there per how many hydrogens, right? The simplest ratio. Whereas the molecular formula is going to be the exact formula that shows all. And I think it's easier to look at some examples to identify those. So if I consider sulfur, I have S8 versus if I have S. S8 is going to be your molecular formula. And that's because it's telling me exactly how many sulfurs make up this particular sample. And here there are 8 sulfurs, but you can simplify that. And the simplified version would be its empirical formula, which is just S, right? It contains just sulfur. So we don't have to always say exactly how many make up the compound. But we know that this particular sample contains just sulfur. So this is our molecular formula, whereas this is our empirical formula. And I know a lot of you guys have already taken AP Bio, and this is a really great application of AP Bio in AP Chemistry. What makes a carbohydrate, right? So glucose, for example, has the formula C6H12O6. This is our molecular formula. And that's because it's telling me exactly how many carbons, how many hydrogens, and how many oxygens make up glucose, right? I could draw the Lewis dot structure for glucose and have a proper structure for that. So if I reduce this to its simplest formula, all of these subscripts are divisible by 6. So 6 divided by 6 gives me 1. 12 divided by 6 gives me 2. And 12 divided by 6 gives me 1. There is 1 carbon per every 2 hydrogens per every 1 oxygen. CH2O, therefore, is our empirical formula. That's the simplest ratio for glucose right here. So, all right, where does that whole carbohydrate thing come into place? Well, anything that has CH2O as its empirical formula is considered a carbohydrate. So if I look at this, this has water in it. That was really not a straight line. I must not have this thing the way I write. But this is a hydrate, right? If you drink water, you're hydrated. So that's our hydrate. And here's the carbo portion of this. It's carbon, right? So every 1 carbon that's bonded to 1 molecule of water, we consider a carbohydrate. And that is one way to determine or to distinguish carbohydrates from other materials, right? Carbohydrates all have the empirical formula CH2O, which is pretty cool. That's one application of empirical versus molecular formulas. And here are just some steps on how to determine an empirical formula and how to determine a molecular formula. I'm not going to talk about the steps, but I'm going to walk you through two problems, and we're going to use these steps simultaneously because, again, I think it's easier to do them than it is to talk about how to do them. So this one says determine the empirical and molecular formulas. So we're going to do that using these steps here. For a compound that gives the following percentages upon analysis. So somebody already did some of the hard work, and they found that using mass spectrometry, this particular compound is 71.65% chlorine by mass. It is 24.27% carbon by mass, and it is 4.0% hydrogen by mass. They also know that the molar mass of the whole compound is 98.96 grams per mole. We want to first determine what's the empirical formula, because it's very easy to determine the empirical formula given these percentages. So what I like to do, again, I always like to make columns or rows just to keep all of my work nice and neat. So I'm going to have a row for chlorine here because the chlorine's my first element. I'm going to have a row for carbon. And I'm going to have a row for hydrogen. That comes next, only because this compound contains each of those elements. Let's look at the first step here. So we want to determine the empirical formula first. If the percent composition is given, we want to change the units of percent to grams. Just makes life a little easier that way. So I'm just going to take these percentages and just change it right to grams. 71.65 grams, therefore 24.27 grams of carbon, and I have 4.07 grams of hydrogen. Makes it easy. If you are not given the percents, if you're given mass, you can actually just skip that step, right? So if you're given mass instead of the percentages, just don't even bother converting it to percent composition. You don't even have to do step one. Next step is divide by the molar mass of the element. So I'm in the chlorine column, so I'm going to divide this mass of chlorine by its molar mass. And chlorine's molar mass is 35.45. And when I do that, I get 2.021. Units of this are moles. So if I have grams divided by grams per mole, right? I can't divide by a fraction, so I would multiply by its reciprocal. Grams, technically over 1, would be this number on top, times the reciprocal of grams per mole is moles per grams. Boom, you could see grams cancels out, and you're left with just units of moles for your answer here. Very good to also consider units and to keep track of your units. Let's do carbon here. Carbon is 12.01 grams per mole. And I'm left with a value of 2.021, actually the same exact value for carbon, or for chlorine, I'm sorry. Hydrogen is 1.01. Divide by that, and I get 4.03. Notice I'm keeping my significant figures here. Step 2 is done. Step 3 says divide by the smallest number of moles. Okay, so I'm going to look at my number of moles. I have 2.021, 2.021, and 4.03. Smallest value is the 2.021. So I'm going to divide all of these by 2.021 moles. So, of course, moles divided by moles gives me a unitless number, which is what I want. When I do that, I like to keep my significant figures again, just because it's going to help you a lot in the end. So 4 sig figs divided by 4 gives me 4. And I get exactly, oh, not moles. Oh boy, I just said units cancel. I'm not following my own rules. And you'll see why keeping those units matters, I think, in the next problem. We don't want to round too much. I get 1.000 again. And here I get 1.99, which is very close to 2, right? So I'm going to round that guy to 2. And these numbers is going to give us how many of that element is present in the compound. So if I look at the last step here, it says write the formula. What this means is that this particular compound contains 1 chlorine. So it's Cl1. It also contains 1 carbon, because that's what that 1 means down here. This contains 1 carbon. And this contains 2 hydrogens, because remember, 1.99 is practically 2. You're going to see an example in the next one where we're not going to round it. We're going to do something else. So I have 2 hydrogens. Now we don't ever write ones, so I'm just going to rewrite this. I have Cl, 1 chlorine, 1 carbon, and 2 hydrogens. Now this gives us the empirical formula. That's the empirical formula. Again, see why I like to type when I can, because that does not look like it says empirical. But that's my simplest formula, okay? So I just determined the empirical formula. That part's done. What I didn't yet determine is what's the molecular formula. And the molecular formula, in order to figure that out, this becomes very important right here. So the molar mass of the whole compound is known to be 98.96. So I'm going to go up here and look at how to determine a molecular formula. So to determine if the empirical formula is the same as the molecular formula, we're going to use the equation. We need the molecular molar mass divided by the empirical molar mass. And that's going to give me some value, right? It's going to be a whole number. And that whole number, that n, is going to tell me what value I need to multiply all of those subscripts by in my empirical formula to get the molecular formula. So it sounds more difficult than it actually is. So let's just dive in and do it here. Let's determine the molar mass of ClCH2. I'm not going to draw this out for you like I did before because you know how to determine the molar mass. Molar mass of this empirical formula is 49.48 grams per mole. So, all right, wonderful. It's telling me in the problem above that the molar mass of the compound is known to be 98.96. So notice how the molecular mass is not the same as the empirical molar mass. And it looks like this should be double. Looks like this is 2 times that, right? Let's just go ahead and plug it into the equation instead of making things a little more complicated than they need to be the first time around. Let's take that molecular molar mass. It's given to me, 98.96. And I'm going to divide that by the empirical molar mass, right, which we determined down here below, is 49.48. And when you solve for that, you get 2. So that means that in the molecular formula, there are double each of those elements that are present. So in the molecular formula, there are 2 chlorines, there are 2 carbons, and there are 4 hydrogens. They are double. So this is the molecular. There we go, molecular formula. That's how we could determine each of these right here. I think the empirical part is a little bit harder than the molecular part, but students always tend to forget how to do the molecular part. But that's why we're going to do practice problems in classes, so we don't have that trouble. And that's it. Without putting anything, extra to these problems, that's the basic idea of it. Let's try sample problem 6 together. A white powder is analyzed and it's found to contain 43.64% phosphorus and 56.36% oxygen by mass. The compound has a molar mass of 283.88 grams per mole. What are the compound's empirical and molecular formulas? Given those percents, we can determine what's the empirical formula. So let's do that first. I'm going to make 2 rows or 2 columns. I have phosphorus and I have oxygen. First step tells me to just change the percents to grams. So phosphorus is 43.64, I'm sorry, grams, and oxygen is 56.36. I'm going to divide both of these by their respective molar masses. So I'm going to divide this 43.64 by phosphorus's molar mass, which is 30.97. And oxygen's is 16. And when I do that, I get 1.409 moles of phosphorus, and I get 3.523 moles of oxygen. Next step is to divide by the lowest number of moles. So 1.409 is clearly smaller, so I'm going to divide both by that number. 1.409 moles. And I get 1.000. Again, keep those sig figs, because of course that's exactly 1. Here, I'm not getting exactly 1. I get 2.5. So you can't have a half of an atom. There's no way that you can have a half. If you have some number that is not very close to a whole number, you have to do a little bit of extra work. When I say extra work, it's not even extra work. You just got to do an extra little step. That's very simple. If you get half values, you want to multiply each of your final values by 2 to get 2 whole numbers, right? So I have a half right here. I can't have a half of an oxygen atom. So I'm going to multiply this value by 2. So I get 2.000, which is 2. And I'm going to multiply this guy by 2, which gives me 5.000. Therefore, my empirical formula is P2O5. Guess what? That's still an empirical formula because I can't reduce 2 and 5 to anything more simple than it already is. So this is still an empirical formula. If for some reason you get a third that's left over, maybe you get 1.33 for one of these. So if you get a 0.33 or a 0.67, you got to multiply all of the values by 3. If for some reason you get a quarter or 3/4 at the end, this is why it's important to keep your significant figures. You want to multiply each of those final values by 4. So keep this in mind. Follow those significant figure rules. Now, if you get a 1.95, let's say, that's practically 2. We're only dealing here if we're at thirds, quarters, or a half. It's when you want to take that value and multiply it by some other subscript or some other value in order to get totally whole numbers. So that's why it's so important to hold those significant figures. So here's my empirical formula. So here's empirical. Let's determine the molecular formula now. So there's my empirical part. It's done. I do have the compound has a molar mass of 283.88. The molar mass for the empirical formula. So if you calculate that, you should find that this is a molar mass of 141.94 grams per mole. I need that in order to determine the molecular formula. So let's take the molar mass of the molecular formula, which is 283.88 milligrams per mole. And I'm going to divide that by the empirical molar mass. And you can really see, even without grabbing a calculator, you could clearly see that this is double, right? So we're going to get a value of 2. You should always get a whole number for this. You're never going to get a half of something. If you do get a half, you did something wrong. But you really don't even need to pull your calculator out for that step. So that means that I have to take my empirical formula and multiply those coefficients by 2, or by those subscripts by 2. So I would have P4O10. So my molecular formula is P4O10. Molecular formula. And that's how you, and that's how you could determine empirical and molecular formulas, especially from percent composition. That's the end of this video. We're going to do lots of practice with this in class. We're going to have a lab where you do something like this as well, especially for mixtures, which is very good. But anyway, let's kind of put this all to use in a really complex problem, also known as a combustion analysis. We're going to do that in the next video. So if you have any questions on this one, make sure you let me know in class. Otherwise, I'll see you in the application part of putting this all together. Bye.